production for the next period, right? So the first, the term within the bracket is the marginal output because of you save more, right? And those output can be used as consumption next period. So that is going to give you extra marginal utility in terms of tomorrow's consumption. Okay, and of course, like this is period T, this is period T plus 1, so we still need to consider the discounted rate there. So that is the Euler equations over there. Okay. Okay, now we are going to change the notation back to C again. And why we are going to do it? Because even we have these equations over there, we still don't know the solutions. Okay, we kind of characterize how the optimal behavior is, but we don't know what exactly the consumption is. Okay, and now we are going to try to kind of approximating like to that answers. Okay, so the reason that we cannot directly see the answer is that now even with these equations here, the only thing we know is K. We don't know K plum. We don't know K double plum. So with one equations, two unknown, there's no way that you can get the answer. Okay, so we turn it back to in terms of C here and writing down these two equations. So the equation 2 is just this from these equations. Okay, but I replace C, replace these terms with C, and these terms with C plum. Okay, and this is just equation 3 is just the law of motions. Okay, and then we set this equals to 1 and this equals to 0, meaning that we're kind of guessing there is a point there is a state. When you reach that state, you are going to stay there forever, because this tells you that the consumption this period and next period are fixed if this equals to 1, right? And if this equals to 0, meaning that the capital you have today and capital you have tomorrow is not going to change. So by setting that equals to 1 and equals 0, we are kind of guess there is a point. When you reach that point, you are going to just stay there forever. You are not going to change. Okay, and does that point exist? Which is yes. So you can actually try to solve the equations here, and you will see that yes, it does exist. Okay, and the solution will be unique as well. Okay, so we will call that state as K star and C star. We call it steady state. Okay, so this is just a guess. Okay. So because this question is too complicated, we don't know how to solve it, but we start our first guess is saying that maybe there is a state. Once we reach that state, we are going to stay there forever. Okay, then the following question is that will we reach that state or not? Okay, so that's why we have this phase diagram here. So how to read this graph? So the blue line here, we start with, okay, so axis. So the x-axis is the capital stock, and y-axis is the consumption, right? Then the black dashed line is the non-zero, non-negative consumption constraint, that you cannot have the negative consumption. And the yellow line yellow dashed line is the resource constraint, meaning that your consumption cannot pass a certain, so there's an upper bound over there. There's no way you can consume like infinite final good. So there's a constraint over there. Then is the blue line, blue solid line here is the unchanged k functions, which is here. When you say this equation equals to 0, on your right is actually a function of k and c, right? So you will have these functions look like this one, okay? And says that if you consume, like if your point is, let's say, above this blue line, it's going to push you backward. How to interpret it? Go back to these equations here. Okay, so now the blue line is when it equals to 0. And when it is above that blue line, then that means your consumption is actually above the required C that we're going to make the capital unchanged. When you consume more than that threshold, then that means you are going to decrease your capital tomorrow. Okay, does that make sense to you? So that's why this is a line tells you that, okay, so if I have, for example, k equals to 2 right now in this period, if I want to make tomorrow's capital stock fixed at 2 as well, I need to consume to this point. Okay, and if we consume more than that, what will happen? Like your capital stock will decrease, right? So that's why, like when you goes up here, the capital stock will decrease for the next period. That's how to read this graph. So vice versa, if you consume less than this threshold, what will happen for the next period? Your capital stock will increase. So that's why you can see the blue arrows point that way, meaning that if you consume at this point, that you are going to increase your capital accumulation, like capital stock for the next period. Okay, so that's how you read this graph. Okay, then the red line here. Okay, so red line is the unchanged consumption, which is when we set the equation 2 equals to 1. Okay, you will have this graph, this red functions here, and the interpretation is quite similar. So you can play with it, and the idea is that when you consumed at the right side of that graph, then you are going to decrease your consumptions and for the next period. And if you are on the left-hand side, then you are going to increase your consumption for tomorrow. Okay, and it's like vectors. So like with 2 vectors there, you know that if the point is in this area, then it's going to go that direction, right? If the point is at this area, then it's going to that direction, which is pointed by the black arrow over there. Then you realize one thing. If I really says that I have the capital K equals to 6 here, okay, and if I really pick out the point here at this area, then what will happen? It's going to lead me to go to the boundary conditions, which is non-negative. It's going to violate the non-negative consumption, right? That means any point in this area would not be an optimal solution, would not be an optimal consumption path, because it's going to lead you to violate the non-negative consumption constraint. So if you have k equals to 6, then you have to consume above that blue line. And by reaching that area, like some point in that area, that is going to lead you to actually to the steady state, which is purple square over there. Okay. Same, if you are at this area, you cannot go to that the area above, right? You have to stay here. And there's a point for a given state k, there's a point that is going to lead you to that steady state. So yes, we do have solutions. For a given positive initial capital there's an optimal path that will lead you to the steady state over there. Okay. The proof is kind of complicated, but this is the illustrations, and hope you can get the idea. And with that, with this graph, what we have to do is actually to figure out the initial consumption C0 is. Because once we pick that, then it tells us, the black arrows will lead us to the next state, and next state will lead you to the 2 state later by iterated the equation.